In this video, we will see a drop mode operation of a governor. A governor can basically operate in two modes. One is isochronous mode. Second one is drop mode. So we will be discussing drop mode operation here. In isochronous mode, the frequency of the generator will be kept constant irrespective of the change in load, and that is not practically used in interconnected power systems. So we will be discussing drop based governor that is more commonly used. So in what is drop? Drop is the decrease in speed or frequency as the power output power or load is increased. So you can see in this diagram at nominal power P0, output power P0, the frequency output of generator is omega 0. So here the drop characteristics passes through this operating point, and at no load it is having some higher frequency, and as you load the machine the frequency is linearly decreasing. So the speed drop is decreasing speed or frequency as shown here by this straight line. So I have marked it here. When the load changes by an amount delta P, the frequency changes by an amount delta F. So this slope of this straight line is delta Y by delta X, that is delta F by delta P, and that is that is denoted by the symbol R, and it is known as steady state speed regulation of the governor. So R is equal to change in frequency by change in power output. Okay. So R is the slope of the speed drop characteristics, and the speed drops as load increases from no load to full load. So we will see some numerical examples to familiarize this concept. So in this first question, there are two identical machines, 1 and 2, and they have drop characteristics with the 5% and 2% speed regulation. So what are these numbers? So this is the R value of first governor, that is R1, or drop speed regulation value of first governor, that is 5%. Then the speed regulation value R2 of the second generator is 2%. Then they share an initial load of 100 megawatt equally. So the total load is initially 100 megawatt and they are sharing it equally. Now and that sharing is happening at nominal frequency. If there is an increase of 35 megawatt in the load, how the system will behave? Okay, if you suddenly increase the load by 35 megawatt, what proportion of the load will be taken by machine 1 and what is the amount taken by machine 2? That is what we have to find out. So the data given is speed regulation of first machine is R1 equal to 5%, that is 0.05. R2 is 2%, 0.02. Now the total load change is delta P, that is equal to load change in machine 1 plus load change in machine 2. Load change taken up by machine 1 plus load change taken up by machine 2, delta P1 plus delta P2, and it is given that total load change is 35 megawatt. So delta P1 plus delta P2 is 35 megawatt. And from the definition of speed regulation, we know that R1 is delta F by delta P1. So since the two generators are running in parallel, both are connected to the same bus, so the frequency is a common parameter. Machine 1 frequency and machine 2 frequency will be same, but the power output, change in power output of the two machines may or may not be equal depending upon their speed regulation characteristics and the ratings. Okay, so here the ratings are different. The ratings are identical, two identical machines. Okay, so the two machines are identical, and their speed drop characteristics are different. If they were both 5%, then they could have shared the load equally, but one is having 5% speed regulation, the other governor has 2% regulation, so the load sharing will not be equal. So R1 is delta F by delta P1, so delta F is R1 into delta P1. Similarly, delta F by delta P2 is R2, so delta F is R2 into delta P2. Now delta F is you can equate the right hand side because the left hand side is same. So R1 delta P1 equal to R2 delta P2, and delta P2 is nothing but 35 minus delta P1 because sum of the loads is 35. Now this is a simple equation. you can solve for delta P1. So you will get delta P1 as 0.02 into 35. That comes around 10 megawatt. 0.02 into 35 divided by 0.05 plus 0.02, that is 10 megawatt. Similarly, delta P2 is 35 minus delta P1, that is 25 megawatt. So this is how we can solve this problem. Now we can consider the example with the two different machines, two similar machines. Okay, two machines with different ratings operate in parallel, but the ratings are different. Here they are supplying a common load of 400 megawatt. The capacities of the machines are different. One is 200 megawatt, the other one is 500 megawatt. Each has a droop characteristics of 4%. Now the droop characteristics is same for both machines. It is 4%. Now their governors are adjusted so that the frequency is 100% on full load. Okay, the governors are adjusted such that the frequency is 100% on full load. That means the on full load, that is 0 to full load. At full load you are having, at this point, at no load you are having some higher frequency, and as the load increases to full load you will reach nominal frequency f0. So at this point frequency will be nominal, and at this point frequency will be somewhat greater, f0 plus something. Okay, then when the machine is loaded to the full extent, frequency will drop by this much, and that amount is 4%. Okay, 4% of the rated frequency, that is that may be 50 hertz. Okay, so here it is given, it is 50 hertz. Now we have to calculate the total load shared by each machine. So in machine 1 we can draw a droop characteristics like this. This is the power output of machine 1. This is the change in frequency of machine 1. So it is given that the frequency changes by 4%. This is the total change in frequency as the machine is loaded from 0 to full load. So it is 200 megawatt machine. So when you increase the load by 200 megawatt, frequency will sharply linearly decrease by 4%. Similarly, in the second machine also, when you go from no load to full load, frequency decreases by 4%, but here the rating is different, 500 megawatt. Now when these two machines are operating in parallel, they should share a common frequency. Suppose that common frequency is at this value. So I have drawn a different figure. So at this point now the machine is operating. So the load shared by the machine 1 is X, is given by X. Okay. So what will be the load shared by machine 2? Total load minus X. Total load is, how much is the total load? Let us check. Total load is 400 megawatt. Okay. So 400 out of 400, X megawatt is shared by first machine. So remaining 400 minus X will be shared by the second machine, and both will be having the same frequency. So this change in frequency from no load will be same, delta. This will be delta F, and this is also delta F. So if you apply similar triangles property here, this is for this triangle, you can write delta F by X equal to, if you consider the bigger triangle, it is 4% by 200. 4% is 0.04 divided by 200. So that is our first equation. Delta F this side by this side is equal to 4% by 200. Similarly, in the next generator, you can apply this principle. Here delta F by 400 minus X for the smaller triangle, and for the bigger triangle it is 4% by 500. So we got two equations and we have two unknowns. So if you divide the equations 1 by 2, delta F will get cancelled. You will get 400 minus X by X equal to this 2.5. So you can solve for X, and your X will turn out to be 114 megawatt, 114.28 megawatt. So the load shared by machine 1 is 114.28 megawatt. So the rest of the load will be shared by machine 2. So the load shared by generator 1 will be this, generator 2 will be 400 minus this number. So you will get the load share. Now delta F you can calculate by plugging this value in the previous equation number 1. Here X is 114.28. So you substitute and find out delta F. So delta F turns out to be 0.0228. You can work out this number. So delta F is the change in frequency, that is 0.0228 per unit, but it is given that nominal frequency is at full load. At full load, the machine is having nominal frequency, and this change is 4%. So at no load, this frequency will be 1.04 per unit. So from 1.04 per unit, your frequency decreases by 0.0228 per unit. So what is the current frequency? 1.04 minus 0.0228 into nominal frequency 50. That will be the frequency then. Okay, so you can go through these examples. I will share one more example in our group. You can solve that. Okay, so thank you.